Yeah, good. Okay, I picked up a microphone, so maybe now it's better. Also in the back of the room. There was a question during the break. Of course, this is the result at the end of the time interval, right? Because that is the number we are interested in, with step size h and with step size h over 2. So it would be a bit confusing with the index and so on. Okay, so this we have seen different methods. We have seen how a truncation error, how we can estimate the truncation error of the method, the error in our result. However, there remains a problem, and that is a thing which we call stability. So not only do we have to be sure that the errors are small, but stability means what happens with previous made errors. Previous made errors. And that's a little bit like you committed a felony, and then you are convicted, and then after your conviction you're free. I mean, you should you're free of all your sins, and you can continue with a blank slate. That is the idea. And that is the same idea here, that you make a small error in an integration step, and of course that error is within your result. And now you hope that this error will die out, that when you continue your calculation that the error will not be propagated. You can imagine that it happens that the error gets propagated, that it becomes bigger and bigger and bigger. People say, oh yeah, he was convicted, yeah, well, you shouldn't hire him, and then it all gets worse and worse and worse, and then that's the end of you. And we don't want that. So now we're going to investigate that. So we're going to investigate the stability of the method, because it's very tied to what type of method do we use, by using a very generic differential equation. So we have to pick a differential equation where we say, well, that's so general, that's such a general differential equation, and I pick this one. I say y dot is lambda times y. Now most of you would think, yeah, come on. That's one of the simplest differential equations. So why do you take that one? And maybe you should put a sine or a cosine or exponential or some weird function in it. Well, actually, in a vicinity of a function, the function usually behaves in a sort of a linear way, and the constant, the lambda, can be complex. So lambda can be a complex number. And why do I say that? Because, well, the solution of this equation, of course, the solution of that differential equation, everybody knows the solution, that is y is e to the power lambda t. and maybe some constant somewhere, whatever. Now you would say, oh, then you can only get solutions like this, growing for lambda being positive, or decaying, so this is time, for lambda being negative. Well, not necessarily, because with lambda being complex, if lambda is something like a plus bi, then the I, you get e to the power bit, and according to Euler, that is, cosine and sine. So I think cosine bt plus I sine bt. Anyway, the point I want to make is you get oscillatory solutions. So you get all solutions of this form. And since it's the product of these two, this times this one, you finally can get solutions from either this, so oscillatory growing, or oscillatory stable, or oscillatory decaying. So that's a very rich family of solutions which we actually find in our dynamics usually. Either we find a decaying or a growing solution, or we find an oscillatory solution. So that makes sense. So actually the differential equation is just fit for the job. Okay, fit for the job. Of course, if you look at a standard mechanical system, like this mass spring damper system, M, K, and C, then the differential equation is, of course, sum of the forces is mass times acceleration, and these are restoring forces. So if this is the displacement x, then if you pull, then the spring pulls back, and if you have a velocity, then the damper pulls back. So you get minus kx minus cx dot equals mass times acceleration, and we get our famous differential equation like this. And of course, we know we can rewrite it in another form by saying, oh, that's x double dot plus 2 beta omega 0 x dot plus omega 0 squared x is 0. Just by dividing by m and introducing new constants. And the new constants are the eigenfrequency omega squared is k over m. And I always have trouble with the other one, so I just write 2 beta omega 0 is c over m. And then what c and beta are, you just have to fill in the gaps. So 2 new constants. Well, anyway, why do I write it like that? Because the eigenvalue, so the solution of this one, if we say x is some x0 e to the power lambda t, then we get lambda squared plus 2 beta omega 0 lambda plus omega 0 squared times some amplitude e to the power lambda t is 0. Now, when does this hold? Well, if it is for all t, then okay, then either x0 should be 0. Well, that's what we call not so interesting solution, right? This was the not so interesting solution. Nothing happens, right? Or the other one is, and that's a bit strange, we don't get a solution, but we get a characteristic equation. And that's always the case in dynamics. So you get an intermediate problem. So you think, oh, now I find the solution. No, not yet. Hold your horses. So from this we can solve. If this is 0, then we fulfill a characteristic equation. And then from that we can solve these eigenvalues. Lambda 1, 2 is minus beta omega 0 plus or minus square root 1 minus beta squared omega 0 I. And then we see, oh yeah, these are of the form a plus bi. What I posed in the beginning, this is an interesting equation because complex eigenvalues encompass all our solutions, and now I prove to you, yes, if you have a mechanical systems, we have these complex eigenvalues. You can even say the real part is like the damping part, and the imaginary part is the oscillating frequency. Okay, having said that, we go back to our test equation. So the test equation is okay. Now what are we going to do with our test equation? So remember, we want to know what happens with errors. So we say y is the true solution plus the truncation error, right? Then if we have this test equation, plus we have y dot is lambda times y, we want to know how does the error behave. Well, the error is also a function of time. Everything is a function of time. So we can differentiate this. So the y dot is the derivative of the true answer plus epsilon dot. Then we put that in the equation and we get true answer dot plus epsilon dot is lambda times y plus epsilon. Of course, we can subtract our initial, where is it? Y dot is lambda y hat, and then we remain the differential equation for our error. Well, the differential equation for our error is just the same as our original one. That was the only thing I wanted to prove. So if we want to look at the error behavior, we can just look at the behavior of this function ourselves. Okay, so this is the error behavior, fulfills that equation. Now, what are we going to do? If this is the error equation, we know already if lambda, if the real part of lambda is positive, then whatever happens, errors will always grow. I mean, that's in the equation. Yeah? So we call that the whole system is stable on a fixed interval. Yeah? If we have a finite time, then we have a finite value, a finite growth. However, if the real part is negative, then we say, well, it's unconditionally stable because everything will always die out. Yeah? So we call it unconditional. There are no conditions. Unconditional stable. Okay, having said that, let's go back to our method. So we have our test equation, yeah, and of course the test equation is a y dot is lambda times y. Of course we think in errors, but I don't want to write everything with epsilon. I stick to the function itself. But with y we mean actually the error. So we have the test equation, and then we have our method. And our method in this case, for instance, say we take Euler. And then the method just says yn plus 1 equals yn plus h times this derivative at t n yn. Now we fill in our test equation here. Yeah? So we get yn plus 1 equals yn plus h lambda times yn. Which we can then write as yn plus 1 equals 1 plus h lambda times yn. Now, if we want errors not to propagate, we call this we call this an amplification factor. Amplification factor, and usually denoted by C lambda h. If we want that, if we want errors not to grow, remember epsilon n plus 1 goes exactly the same as this one. If we do not want an error to grow, then this 1 plus h lambda should be less than 1. But remember, lambda was a complex number, so we should say that the absolute value of this should be less than 1. Because we have complex is two-dimensional and you have to take the norm. Okay. So how does that look with this? So we get the absolute value of 1 plus a plus h times a plus h times bi should be less than 1. Well, we can draw that maybe in the complex plane, right? So we have here the complex plane. And so we have here the real part of h lambda, which is ha, and here we have the imaginary part of h lambda, which is hb. And now we have to find, well, to find this area, because it's an area, it's an inequality. We first try to solve, of course, what is the boundary. So 1 plus ha plus hbi is equal to 1. So that should be a curve somewhere in this plane. Any idea what the curve is? Yeah, it's a circle, huh? And it's shifted a little bit. So, yeah, with the +1, it's shifted to the left. Because if A is -1, you are at the center. Something like that. So, this should be the center. So this is -2, this is -1. And then this should be I, of course, and this is -I. And then we get a nice circle around here. Now, the statement is, so it should be stable, if we fulfill this. So the stable area is apparently this. So all h lambda, which are within this area, make sure that the method we use, the Euler method, will result in stable result, that errors will not propagate. So it's only about the method. So you have to know what the eigenvalue of your system is, and then you can pick your step size, right? For instance, yeah, if you have a real eigenvalue, then the lambda should be if lambda is pure real, then well, it can be between 0. So h lambda can be between this, and then apparently the maximum step size you can take. First of all, to be stable, lambda has to be negative. Yeah, negative step size is not what I'm talking about. Will be another solution. And the other thing is, of course, that the step size should be smaller than 2 over lambda. So that's for real ones. So for these type of systems which have decaying behavior. If it's a non-decaying behavior, you're somewhere in this area and on this axis for the real part, and yeah, it's only stable within a finite region. It's conditionally stable. The other solution, actually interesting. Let's say we look at a simple pendulum without any damping in a gravity field, length L, mass m. Then we know that the eigenvalues are something like plus or minus the square root of g over L times I, something like that. G over L being the eigenfrequency squared, and then well, the point I want to make, it's a pure imaginary thing, meaning that they live on this axis. Is any point on this axis in the stable region? Yeah, 0. Okay, so we take a step size h is 0. That's a stable result. Yeah, that's true. But nothing happens, right? If we take a step size of 0, then we just remain where we are. Okay. Meaning that this oscillatory system, you cannot solve that in a stable manner with an Euler scheme. So if you use an Euler scheme on this differential equation, you do the numerical integration, and you want to have more accurate result, you refine your step, finally what will happen is it will grow. I mean, errors will get propagated. So finally you will get this. Yeah? So that doesn't work very well. Is there a way to solve that? Well, maybe higher order methods work, right? We have seen Hoyne. Hoyne was a nice method. If we look at Hoyne, and remember the scheme was something like that, we had an approximation plus h times the function at tn, yn, and then the real value was this average. So we took this one, h over 2. We have the initial derivative, tn, yn, plus we take the derivative at tn plus h, and then at this star, this approximate value. Of course, with this we can again do this differential equation, y dot is lambda y, and put everything in. And then finally we get the following expression. We get yn plus 1 equals yn plus h lambda over 2 yn plus h lambda over 2 yn plus h squared lambda squared over 2 yn. So that's when you put everything into the equation and just write it out. Or in other words, the amplification looks like this. It's all yn. It's a 1, of course, from this guy. Then we take these together, so plus h and then plus h lambda plus h lambda squared over 2. So apparently the multiplication factor c h lambda is 1 plus h lambda plus h lambda squared over 2. Well, that does not surprise me so much. It looks a lot like the Taylor expansion of a function. But now let's look at the stability condition. So we have that the absolute value of this should be less than 1. So again we go to the complex plane, because this lambda can be just this a plus bi. And then if we plot that in the complex plane, so real part of h lambda and here the imaginary part of h lambda, then what do we get? Well, you can let me write it down again. 1 plus h lambda plus h lambda squared over 2 equals 1. I'm going to draw the boundary first. If you find this hard, then usually what we do, we first take only real numbers and say where does it is, and then we take imaginary numbers. But you can also use MATLAB, actually, which is sort of nice to say, hey, let's make a contour plot. Let's discretize in x and y, and then I have this function, and let's draw the contour. That's super easy, actually. And then when you do that, you get the following form. So this is -1, this is -2, yeah? And we get something like this. That was not nice. Like this. And then, of course, it's identical at the bottom. Well, identical at the bottom, something like this. And the top here is, I think, square root 3. Yeah. I, and here the bottom is minus square root 3i. And, of course, everything which is within this area is stable. Now, what we hoped for, we did not achieve, right? So, again, pure oscillatory solutions are not within a stable region, and you will see if you use this Hoyne method, then slowly your errors will grow and grow, and your results will not get accurate. The area is a bit larger, so you can take a bit larger step sizes, but even for real systems you can't. It's the same. It's the same 2, so it is more accurate. But we can continue our quest. I mean, we have a first order system, a first order method, Euler. We have a second order method, Hoyne. We just can continue. And now I make a jump forward, because now I go to a Runge-Kutta 4. And I skipped the third order on purpose, because that's not so well used for various reasons, which I will not explain today. But the next one, this one, that's a super famous one. I think everybody is using that. The acronym is RK4. If you look in the lecture notes, you can see the pictures of Mr. Runge and Mr. Kutta. They were mathematicians in Germany. Now the history is such that Runge started, I had the other date wrong. Runge started in 1895 with the first generalization of Euler methods, Euler. Then Hoyne continued in 1900 by coming up with this more refined method, the Hoyne method. And then Kutta finished the job by saying, hey, actually this is a whole family of explicit methods, which we later called the explicit Runge-Kutta methods, but before that they couldn't call it that. And then in a nice paper in 1901, he showed all the different methods with all the different orders with their accuracy and so on. So it is called Runge-Kutta, but it should be called Runge-Hoyne-Kutta. Well, that's how history goes, right? How does it go? Well, the Runge-Kutta, I think almost everybody knows that scheme. there are four things which you have to calculate. K1, that's a derivative at T1 and I1. So that's just the normal derivative we always do at the beginning of the step. Then I calculate the derivative, and I do that halfway. So I say Tn plus h over 2. And then I need an approximation, of course, for where is that point. Well, I have a derivative. I have K1. So I can say, well, I'm going to add h over 2 K1. That's a nice approximation for that point. And then you say, well, maybe you made a small error. Let's redo it. So again at this point, but now as a derivative, I don't take K1, but I take K2, because my gut feeling is that that's probably a better approximation. And of course we have to get at the end, so I say, well, the end point, t plus h, I take yn. What for approximation? What derivative do I take? K3, and then h times K3, apparently. So this is a very natural way to calculate all these derivatives. And then a new value, yn plus 1 equals yn plus h over 6, yeah. And then K1 plus 2K2 plus 2K3 plus K4. And it's a very balanced, symmetric scheme. All the intermediate derivatives are in the end result. And we can immediately say that the accuracy of this, the truncation error, is of course 1 order higher than the number of derivatives, so 5. Now the amplification factor, I won't burden you with the derivative of that, but the amplification factor takes on this form: 1 plus h lambda plus 1 over 2 h lambda squared plus 1 over 6 h lambda to the power 3 plus last name, yeah, of course, stupid, 4 times 6, of course, h lambda 4. Now plotting this by hand in a complex plane, that is undoable. I have no clue how to do that. So we quickly go to MATLAB, and then if we use MATLAB to find the boundary, to find ch lambda is 1, then the following figure emerges. So this is 1, 2, 3, this is minus 3, 1, 2, 3, minus 1, and yeah, it's symmetric. We'll make it symmetric in a moment. It starts somewhere here, and then it goes like this, and this, and then it goes like this, and this. And now I'm going to do a trick, otherwise it's not nice. So this is the stability, the boundary. So this is a real part of h lambda, and this is the imaginary part of h lambda. The value here is 2.8. To be specific, it's 2 square root 2, I believe. I, of course. And here minus 2.8, and here the same minus 2.8. And of course, the whole region within this gives you stable results. And I am happy now. Why am I happy? Yeah, here we have, so the pure oscillatory solutions are in this region. So now for even pure oscillatory systems, lambda plus or minus omega times I can say that my step size should be less or equal to 2.8, 2.8 times omega, or divided by omega, sorry, by this omega. So that is super cool. So now if we use this system, apparently these errors will disappear. Remains of course the question that, yeah, in a way we have a little bit sort of artificial damping in our system, because even for unstable systems, so you're not on the axis but you're a little bit off, so we are in a system which shows exponential growth, the method has a tendency to damp out stuff. And that's actually a super interesting question. So how can you check if your system is damping out energy?
Plot the kinetic and potential energy and see if it decreases with time.
Yes, you can do that. You can even go one step further. You can say, oh, let's look at one step. And let's take an archetype of a mechanical system for which we know there is no damping, just a pure oscillatory system. Differential equation is super simple. We just put that in our method. We calculate the energy at the beginning. We estimate what the new values are. And then we calculate the energy at the end. And then we'll check, is there energy lost? And what is the amount? And how does it behave? What is the order in which the energy disappears? That's a super interesting thing, for which you can definitely earn bonus points. So if somebody feels the urge to do this, please do, hand it in, and you get a bonus on your homework. Definitely. And more than one bonus point, I guess, because it's a serious amount of work, I guess. Well, okay, that's not the topic, so the important thing is I'm happy because now oscillatory systems I can integrate numerically stable. What we have seen until now is we have peaked in the box of numerical integration methods. We just opened the lid like minute and looked inside and closed it, because there are so many methods. Until now we only looked at explicit Runge-Kutta method. You have implicit numerical integration, which have a beautiful hallmark that they are able to damp out high frequency stuff. So if you have a system with high frequencies and low frequencies, a mix, so with fast transients, which all decay, then the problem is the fast transients you have to follow in a normal Euler-Hoyne or RK scheme, and your step size becomes very small. But with an implicit scheme, your step size can be large, and you get rid of that. But the downside is it's implicit. You have to solve always, for every numerical integration step, a set of nonlinear equations. Yeah, question?
Why no one of them could change age during the...
Oh, yeah, we do. So in the lecture notes, I show that with the relation between these explicit schemes and ODE 4.5 and ODE 2.3 from MATLAB, and they have an adapting step size. And I'll show also in the lecture notes how this works, because ODE 2.3 is a third order scheme, but it does also error estimate. And because it does error estimate, by taking one extra step, it's able to say, oh, we have to refine the step because the accuracy, it's not the accuracy you want. And the same for 4.5. It is in the lecture notes. If you're interested, check it out. You can read all about that. There's also a way how to interpolate the results, because with these K1 until K4, you can interpolate the function somewhere in between. And if you want to detect, for instance, contact, then sometimes you just go through the floor, because in the next step you're already under the floor, from above to under. And you want to find what is exactly the time when I reach when I hit the floor. With the interpolation available in ODE 2.3 and 4.5, you're able to do that within the accuracy of your results. But that's all in the lecture notes. I'm not going to talk about it now. There are even methods which are specially apt for second order systems, because remember, in the second order system we have a very stupid differential equation. Q dot is P. That's the most simplest differential equation you have. And you can use that to your advantage in your numerical scheme. Also in the notes. What I want to talk about for the last quarter is about global error estimate. I want to revisit that. So, global error estimate. And especially, what do you do in practice? What to do in practice? What to do in practice? So what do we do in practice? Well, we know, of course, that this error is something like, what did I say? Yeah, C1 times h to the power p. That is the global error we make. And then for p is 1, no, I should do it the other way around. Then for Euler, we have p is 1, Hoyne, this is global error, we have p is 2, and for the RK4 we have p is 5 minus 1, 4. However, if you then do your estimates on the error, and remember we did something like this, that the estimate is something like y with an h minus y with an h over 2. That's what we calculate for different step sizes at a fixed time t, of course. If you then plot that in a graph, so this is the step size, and here is this difference between these two successive step sizes we use, then you see that while you are making the step size smaller, things are getting good. Like, oh yeah, I want a sort of a minimal error actually, and then suddenly this happens. Totally contrary to what you expect. Like, hey, what the heck? I was refining my step size and the result is getting worse. So what is going on? Yeah. Yeah. In a computer, so not only has the method a truncation error, but we have a finite word length in our computer. So round-off errors are also present, and they are, well, some constant, C2, it's a small number, and that's it. And how small is the number? Well, if you look in MATLAB, for instance, then the round-off error C2 is approximately, we call that EPS, and that's 10 to the minus 16 or something like that. So that's for double precision. Yeah. And if you want to have triple precision, it's 10 to the minus 24 or something like that, and you want a quadratic, well, you can continue whatever you want, but there's always a round-off error because we have a finite word length in the computer. Now, we do make not only one of these round-off errors, but how many? Yeah, the number of steps we take on a finite interval is t over h. So for the round-off error, finally, the round-off error we make is some constant C2 times 1 over h. So this is round-off error. So the net error, the total error, takes this form, C1 h to the power p plus some C2 1 over h. And the 1 over h thing is what's happening here. So if you make it smaller, 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 suddenly this error is kicking in. So apparently it's a sum of two errors. If this is a very small number. If the step size is not too small, you won't notice it compared to this one. But the moment the step size gets smaller and smaller, this doesn't become important, but this is the important part. So it's a trade-off between the two. And of course, if you plot that, for instance, this was an example where I tried to do the Hoyne method, where the p is 2, so this should be like a parabola approximately, and then this should be like a line with minus 1, something like this, I don't know. Anyway, the best way actually to plot this is not on a linear scale, but on a log-log scale, of course. So if we now plot the log of this difference as a function of a log of the step size, should be log, not talk, log of the step size, then of course we get a line in this region, we get a line which has an arctangent p, the slope of that one, because that's this part, and because C2 is a very small number, this only kicks in somewhere here, and here we have then a line, 45 degrees, right? So minus 1 arctangent minus 1. And then if you plot your results, it's the sum of these two, so you get something like you're here on the line, and then the other one kicks in, and something like that. That is approximately what you would see in practice. And that's also what we do in practice. So we refine our step size, we calculate the difference between the results, and then we plot that on a log and log scale. And apparently there is also a minimum, there's E minimum, which has to do, of course, with the method and with the computer you use and the problem at hand. But there is some, you cannot get a smaller error than some value. And there's apparently also this H optimal, some optimal step size where you get this minimal error. Okay, as an example, I like to talk a little bit about monkeys. Monkey business. Does anybody know what gibbon brachiating is? Gibbon brachiating? No? Okay, let's see. Let's see if it works. So this is a gibbon, and he's swinging, and it's a way of locomotion, right? So instead of using his feet on the ground, he uses his arms on the poles, on the air. And the beauty of it is, oh no, I don't want this, go back. What is the beauty? Well, when he grabs with his hand, the velocity by which he grabs is almost zero. So there's no impact. So there are no energy losses when he makes contact with the fixed world. Opposed to when we are walking. We put our foot on the ground and there's bang, there's an impact, so you lose energy. In this system, you can move around without losing energy. You can do that also in walking, but then you have to put your foot with zero velocity on the ground. You can. Take some time, but it's doable, right? Now, this is of course, from a mechanical point of view, super interesting, because you can make a very simple mechanical model, even like two arms and a point mass, and you say, well, let the thing swing. There's a phase of contact, and then it goes in the air, and that's actually the topic of the research which Mario Gomez did, and he wrote a nice paper on it. Gomez from Cornell, advised by my friend Andy Ruina, and he was interested in this cyclic motion. And here we see a nice way. You grab onto the ceiling, you swing, and then you quickly with your other hand grab onto the ceiling and you swing, or we go the other way around. This is time. But you can also do a flight phase, as you saw with the gibbon. So he swings, he lets go, and then you have a parabolic flight, and then you grab on again. But you can also do this, like parabolic flight, and then and there are all kinds of ways to do that, right? So you have a whole family of cyclic solutions, which we as theoretical and somewhat applied engineers love. Yeah. So application is this, and then the model here, a simple model. You can do a point mass, but you can also do an extended body, one rigid body. Then of course you can continue. You can say instead of one rigid body, I do two rigid bodies, etc., etc. Well, you get the picture. You can make more complex models and look for cyclic solutions. Yeah. You can construct a mechanism with this, in the sense that you can apply to. If you give it the initial conditions, it will do what it will do, because it's a cyclic motion. There's no energy loss, and it will just do what it does. If it does work, you lose energy and you have to put in some. So, but it's a nice cyclic motion. Now, Mario Gomez was finding these cyclic solutions, and you can imagine that he has to do numerical integration, because you cannot solve that analytically. And you can also imagine that he has to know his results very accurately to say, yes, this is a cyclic motion. And moreover, yes, it is stable. That's even a deeper question. Is the cyclic motion stable, yes or no? What is the basis of attraction? Okay, in doing that, he made this nice plot. Let's get rid of this for a moment. So on the horizontal side, you see a log of the step size, and on the vertical, you see a log of the estimated error. And here you see these numbers. Well, this is Euler's step. That's very slowly going down. you say, oh, that should be, the slope should be 1. Well, it is 1 because the scale here is different than here. So this is 1 and this is 2. So this, oh, don't do that. This should be a 1 by 1 thing, which is approximately correct for the Euler. And then we see other methods, 4th order, 5th order, 6th order. And we see them decaying with decaying step size. There should be a minus here always, and here also a minus, there's a small error. But we see when the step size decreases that you get more accurate result, but you also see that you hit a floor, or a floor, the real floor, not the ceiling. And around 10 to the minus 13, apparently. So it has to do with the problem, has to do also with the method. And you also see that if you use Euler, you're never going to make it. It's not going to work. So higher order methods do help. And you also see that you can attain higher accuracy with higher order methods at a larger step size. Yeah. And that all includes, actually, finishes the lecture of today. And this is the homework for next week. Not on the gibbon, on the double pendulum.
What's the maximum error is 10 to the power of minus 4? The maximum, the minimum error.
Apparently 10 to the minus 13. Yeah, approximately for his problem.